All right, so let's take a look at chapter 12, which is just some more advanced features of the TensorFlow Python library. So we've been using it in simple ways, but it does have some fancy features to do advanced machine learning models. So this is Keras is its high-level API, and we've referred to that in some of the projects. And Keras gives you the simple networks for most use cases. Um, And TensorFlow is the low-level API where you can customize it to make more advanced and more complicated models. So you can have customized loss functions or layers or regularizers and so on, rather than using the standard things. Now, it is from Google and powers a bunch of Google products, and it's been open source since 2015. And so it's like NumPy. NumPy is a Python number library to do mathematical calculations on things like tensors, and this has GPU support. And so it's optimized to make things fast, and the graphs can be imported to other environments. So it also implements the AutoDiff that we talked about, which does the differentiation to figure out how to adjust all the parameters to do gradient descent, and provides all the optimizers we've been talking about. And so it has a lot of functions here. Keras is the high level one for learning to do simple tasks. And here's the AutoDiff is gradient tape. You got mathematics doing lots of calculation, and you have pre-processing for audio and images and other things. You've got things to deploy and optimize them here, and special data features and miscellaneous things. This is the low-level API where you can control the processing your machine learning model in great detail in case you want to do something exotic. And there are kernels, and the kernels connect to the fast processors, GPUs or TPUs, which is, of course, very important. For simple models, you can run them on CPUs, but for more complicated models, you need GPUs or TPUs, or these days, NPUs, neural processing units that are faster. So you write Python code, and Keras is usually what you use for the simple ones, or you use the data API. And some of your code might actually call low-level Python, but mostly you run it through these libraries, and that takes it to an execution engine down to kernels, which take it to the hardware. And you could use other languages. You're not particularly limited to Python. Keras TensorFlow is also available for these other languages like C++ and Java, and even JavaScript. All right, so you got TensorBoard for visualization and an extended one to do more complicated projects, and something called TensorFlow Hub, where you can upload and download models. Now, the hub I know is the Hugging Face Hub, which is the place where most people put open source models and you can download them and use them. Apparently, there's a TensorFlow one too, which I don't think I've ever deliberately used. So you can use it like NumPy. So you can import TensorFlow, and then you can define a TensorFlow object, which is going to be an array of floating point numbers. So this is 1, 2, 3, 4, 5, 6. And what it is, it's a two-dimensional array, a tensor, they call it. And so it contains one vector here, 1, 2, 3, a list of numbers, and then another one here, 4, 5, 6. And so if you print it out, it will print it out and then tell you its shape is 2 by 3. There are two lists, and each list contains 3 elements. And the data type inside each one is a 32-bit floating number, which is the default float number there. That the decimal points is how it knows its floating point. So now you can index it. Here's what we defined. And so if you print T00, that will be the 0th element here, which is this list, and the 0th member of the list, which is 1. So that's 1. And when you print it out, it will show you the 1.0, and it will add the shape and the data type. It's still a tensor, that part of it. And here's 1, 1, which is going to be the element number 1 and the item number 1 in the list, which is 5. And you can print this colon means all of them. So it will print all the elements, all the lists, but it's only going to print from 1 to the end. So it's going to print the last 2 elements of each list, which is 2, 3, and 5, 6. That's what this means. The colon means print everything. in that index, and 1: means start at item 1 and go to the end. Now you can do things like this. You can print TF square. So you have the T, remember the raw T was 1, 2, 3, 4, 5, 6. T plus 10 adds 10 to each element, so it's 11, 12, 13, 14, 15, 16. Square will square every element, so it's the square of 1, 2, 3, 4, 5, 6. And you can multiply T times T transpose with matrix multiplication, and that will take a 2x3 tensor and turn it into a 2x2 tensor, combining the elements. Now, there's an issue of type conversions. Here I have 1 plus 2, colon. I'm not quite sure what that's about, but the point is here's a constant of 1 and a constant of 2. And that will work. It prints the tensor 3, shape of 2. So it takes a constant 1 and constant 2 and adds them and becomes 3. Oh, this is just a label for some reason. Oh, I see. Now I finally understand. The label, I'm adding 1 plus 2, but here I'm adding 1.0 to 2. And 1.0 to 2 will crash because you cannot, it's expected to be a float tensor, but it's an int32 tensor. So this is an integer tensor, and this is a floating point tensor, and you can't add them together. Like I've said many times, I spend most of my time in Python converting one data type to another, because you always hit errors like this. So if you want to fix that, you have to cast it. So if you want to add 1 plus 2 this way, if you have a constant 2, you can cast it to type float 32, and now you can add them together. So this will be by default float 32, and this will start as an integer and then be converted to float 32. All right. And also, TF constant means this cannot be changed. So if you define this 1, 2, 3, and 4, 5, 6, and then you try to change the first element to 3, it won't let you because the object doesn't have any assign method because it's a constant. If you want to have a tensor and you want to be able to change the data in there, you have to use variable here. And now it'll define 1, 2, 3, 4, 5, 6, but then I changed the first one to 3, and you can see it change here. Here's the original 1, 2, 3, 4, 5, 6. And after I do the assign command, the first element has changed to 3. So there you can have sparse tensors that are mostly zeros. You can have arrays. You can have ragged tensors with varying sizes along certain dimensions. And you can have tensors that contain strings instead of numbers. You can have sets and queues, more objects that assign a lot of items in ways that are easier to handle for specialized purposes. And then you can make custom models and custom algorithms. So normally you have a loss. Huber loss is the one that has mean squared error and absolute error. You could build it yourself. You could define a function to do whatever you want. Yes, the slides are already up there, Marion. If you want the slides, let me point them out. If you want the slides, they are here on the main machine learning page. Here, there. All the slides are down here in Keynote and PDF format. So that's good. And okay.
Oh, sorry to interrupt, but
yeah,
isn't this number topic 12?
It is 12. I thank you. I'll have to add it. Thank you for telling me. I didn't realize it's not there. Thanks for telling me. Good.
Yeah, thank you.
Yeah. Okay. Anyway, so here's a custom function. You could define this any way you want. And now when you compile it, you tell it, I'm going to use my custom function to measure loss. Remember, loss is the number you're trying to minimize. So you could define a different loss function if you want and specify it when you call the model compile here. And you can customize everything. You can customize the activation function and the initialization, which chooses the initial pseudo-random values, and the regularization function and the constraints. There are default values for all these, but you can define custom functions for all of them for special purposes. So losses are the measure of how wrong your model is, so it will lower the loss. And metrics are used to evaluate a model to report the answers. So those should be easy for a human to understand. To make any sense, the losses might be difficult for humans to interpret, and it doesn't really matter. You can make custom layers like this using lambda functions. This will apply the exponential function to its inputs. So it will change x into e to the x, which is something you might want to do for some exotic circumstance. You can make custom layers if you want to. And you can make custom models, like here's one where in comes data into a dense layer, then you run the same layer 3 times, and then once more, and then you're out. And inside here, each one of those is going to be 2 dense layers, and then a shortcut here that skips over it and adds those together. So it adds the input plus the output of 2 layers together and passes it on. So you can make a complicated model like that with custom code like this. And all right, there's more details. I don't feel like going through it, but that's the idea. Okay, then you can define your losses and metrics. You can measure your loss based on model internals if you want to. You don't have to compare the output of the whole thing to the desired output. You could include other information like weights of hidden layers because you want to make sure those weights don't rise too large or something. And the auto diff works by this gradient tape, which automatically records every operation involving a variable. So it can roll back to the previous layers, the previous values of that variable to figure out the derivative. And here we've got a wide and deep model we saw before. You have input data here, which is normalized, and then passed through a deep model, but also passed right past it. So you take the input and include that with the output of this, both as data for the output layer. And this will require a custom loop. It's not a simple model. And you can also visualize these things. There's an autograph and tracing function, which will draw these sort of block diagrams to try to make it easier to interpret your code. And that's all I wanted to tell you. I'm going to stop this video.